So in the previous classes, we learned how to transform from one coordinate system into another coordinate system. As for example, we can transform from spherical coordinate system to rectangular coordinate system, or from rectangular coordinate system to spherical coordinate system, from cylindrical coordinate to rectangular coordinate system, and from rectangular to cylindrical coordinate system. As for example, x, which is a coordinate of rectangular system, can be transformed into by spherical coordinate system as r sine theta cos phi, y is equal to r cos theta cos phi, and z as r cos theta. This we have already done. It means x is function of r theta phi, y is a function of r theta phi, and z is a function of r theta. We can form inverse transformation also, that is x r square, r can be written as x square plus y square plus z square under root, and so on. So this all we have done. So today, and suppose we have a generalized term, or suppose we have n part, for one particle we require three coordinate system, three coordinates to specify its position space. So for n three particles we will require 3n, and if they are connected by k number of equations, then the degrees of freedom become 3n minus k. So these 3n minus k coordinates, we determine them by a generalized coordinates called q1, q2, qn, q3n minus k. So these are the coordinates to specify 3n particles which are connected, constrained by k number of equations. So these are the generalized term or generalized coordinates, we call them as, because the degrees of freedom are 3n minus k. So this means we can transform, or one can transform from one coordinate, system. Suppose the coordinates are r1, r2, r3, and r3n minus k. Suppose their time also appears, so it's into generalized coordinate system. q1, q2, q3n minus k. So we can express r1 as a function of q1, q2, q3, q3n minus k plus t. Similarly, r2 can be written as r2, q1, q2, q3n minus k into t. And similarly, r3n minus k, r3n minus k, q1, q2, q3n minus k. Or we can inverse transform also. Inverse transformation means you can express q as r1, r2, r3n minus k. Similarly, q2 and q 3n minus k. Okay, so these are the how to transform from one coordinate system into another coordinate system. So what are the requirements for a generalized coordinate? Which coordinate should we choose as generalized in our solving a problem? So three suitable choice of generalized coordinate. Suitable choice of generalized coordinates require that, and we have seen that some problem can be solved in one coordinate system more easily than in other coordinates. As for example, central force problem, it's easier to work in spherical coordinates than in rectangular coordinate system. So in that case, the coordinates there will be spherical coordinate system. So it depends upon the nature of the problem, which coordinate system you have to choose. So the suitable choice of generalized coordinates require that, number one, they specify the configuration of the system. Number two, they must be independent, and the coordinates must be independent, but without violating the constraints, without violating the constraints of the system. And the third, that they must they must satisfy the mathematical calculation. They must satisfy the mathematical calculation. Okay, so which coordinates we taken as generalized, we have to take into account these points. Now the next is, what is virtual displacement? A virtual displacement is imaginable infinitesimally small displacement which does not disturb in the constraints. So the virtual displacement is it's not the actual displacement, it's assumed. This is the virtual displacement, means it's assumed that the system has undergone such displacement. But the displacement will be consistent with the constraints. So any imaginary infinitesimal displacement, any imaginary infinitesimal displacements that does not violate the constraints acting on the system. At that time is called virtual displacement. So this is one definition of virtual displacement. We will do some problem, then we'll understand how the meaning of virtual displacement. What's the use of taking this virtual displacement? Now we have virtual work. These are all virtual work. That is a system having n particles, or say one particle, having having n number of forces acting on it. So the sum of the total force, suppose I means 1, 2, 3, 4 number of forces, product by dot product by the displacement. The dimension of this will be work, and this displacement is virtual, and this is the force acting on the particle. So IF particle. And suppose force F1, so the displacement on sum of these. So this is the summation. So this is called the virtual work. So the dot product of the sum, the dot product of the sum of all the, or you can say the virtual work means this is the virtual work. Delta W is equal to dot sum of the dot products of the force acting and the virtual displacement and the sum total. This is the total work done. This is the virtual work. Now if the system is in equilibrium, if the system is in equilibrium, the sum of the forces acting on them will be 0, so the virtual work will be 0. Now this Fi contains this the force on the ith particle. So suppose Fi can be written as in rigid body, or you can say if the forces are constrained, it is a sum of two forces. Or it is the sum of all the forces acting on this part, that ith particle. It has two parts. This is A. A means active, and this is So this is applied force and this is the constraint force. And this delta W is equal to sum of these F I applied plus constraint dot delta R virtual displacement. It means summation over applied dot delta R I plus constraint force. So this is the virtual work done by the constraint force, and this is the virtual work by the applied force. Now we'll see that since the constraint force does no work, so this will be 0. So the actual is delta W is sum over F I applied dot delta I. So you some question must have arrived in your mind. What's the use of doing all these things, virtual work, virtual displacement? You will see in the problem that what does this do. It means we are transforming our working in from force system to energy system. In the Newton's law we used force. Now we are taking energy. What is an energy? And you will see that in this case all the forces of constraint forces fades out itself, and it's easier to solve problem in this system, in energy system, than in vector system, that is force system, because force is a vector quantity and it must it has to be resolved into components, but energy is easier to solve because energy is a scalar quantity. So now we have just seen that for equilibrium, that is equal to F I dot delta. This is our virtual work. Now when the system is in equilibrium, in delta W is 0. That is, since Fi, all the applied forces comes out to be this, comes out to be Fi applied dot delta I. Now since the system is in equilibrium, all the applied forces on the system is 0. So the work done will be 0. When the system is in it's in motion, and the system is in motion. So the applied force we know from Newton's law. We know that the applied force will produce a rate of change in momentum of the system. From Newton's law, we know that the applied force on the system will produce a rate of change of momentum. Or then we can write this as Fia applied minus Pi, the work done by this. This states that the particles in the system will be in equilibrium under a force equal to we can write this as Fia minus Ei equal to 0. Means the system will be in equilibrium if we apply a reverse rate of change momentum. The applied force minus this portion will give you 0. So the but run will be now will be 0. So this states that the particles in the system will be in equilibrium. Under a force equal to the applied to the actual plus a reversed effective force minus Pi. So we can write that Fi minus Pi dot 0, and the work done in that case will be 0. And this is called the D'Alembert's principle. This equation is called, so this term Fi applied minus this is called the D'Alembert's we will do some problem using virtual work and virtual displacement, and then we will prove the equation of motion. This is the equation of motion, but this is the equation of motion. We will express this equation of motion in generalized coordinates. So the first I brought some problem for you to explain the virtual work and virtual displacement and how they are applied. Suppose we have a cylinder over which two blocks one block, say so it is, suppose this is M2 and this is M1. So first of all we will find the equilibrium case. So this is the center, that this makes an angle theta 2 and this makes an angle theta 1. Okay. So first of all we will do it Newton's method. In the Newton's method we have M2G vertically downward along the tangent, that will be M2G, this is This is theta 2, this is theta 2, so it will be m2g cos theta 2, and here it will be m2g sin theta 2. Similarly, here we have m1g vertically downward in the force of gravity components along the tangent. This will be m1g sin theta 1, because this sorry, so this is theta 2, and here it will be m1g cos theta 1. Right, and it is the tension here in the string. The string is supposed to be massless, though the tensions are same. So from Newton's method, m1g minus mg1g sin theta minus t, m1g sin theta 1 minus t is 0. So the system is equilibrium, no acceleration, no motion. Here, so it is t minus m2g sin theta 2 is equal to 0. Solving this, we will get m1g, m1 sin theta 1 is equal to m2 sin. So this is the condition for the system to be in equilibrium. Now, for equation, if the system is in motion, it's not in equilibrium, the equation of motion. Suppose the system is undergoing acceleration in this direction, so it will be m1g sin theta 1 minus t is equal to m1a, and so the t is putting and m2g sin theta is here. The resultant acceleration is, suppose we are taking along this side, so it is t minus m2g sin theta 2 is equal to m2a. Worked out, you can get acceleration as m1 sin theta 1 minus m2 sin theta 2 times d divided by m1 plus m. So all this we have solved by Newton's method. Now we'll work out by using virtual work. Using a virtual work system or analytical method. This is not the, you can say, the Lagrangian method. So the virtual work. In the virtual work, we have with our definition, we have sum over forces and displacement. So the forces acting on this and the displacement. Now suppose so two forces acts on this, m2g sin theta 2 minus t. This is the resultant force acting on m2, and suppose delta r2 is its displacement, and suppose the displacement is somewhere. This is the virtual displacement, delta r2 plus the forces acting on this particle. So the forces acting on this particle is m1g sin theta plus t dot delta r1. Suppose this is displacement is delta r1 I am removing these things so that so the displacement here is in this direction, and this displacement, virtual displacement is in this direction. Now you can take the component of virtual displacement along the tangent perpendicular to the tangent. Here also you can take the components along the tangent and perpendicular to the tangent. So this will give you m2g sine theta 2 so we are writing as dr perpendicular component, dr1 perpendicular. It means the perpendicular component on this plane as, and parallel component as, okay, or we can write this tangential and perpendicular. So T for perpendicular, T for tangential. Similarly here dr2 we have two components, a perpendicular component and tangential component. So this has two components, right? So m1g sine theta dot delta r 2 perpendicular component, P for perpendicular, T for tangential, okay, plus m2g sine theta 2 dot delta r 2 tangential component, plus T has T dot delta r perpendicular component, T delta r 2 tangential component. So this we have done. Similarly for this m1 g sine theta 1 times say perpendicular component of this, and then they are 1 e plus m1g sine theta 1 dot delta r1 tangential plus T dot delta r1 perpendicular plus T times delta r1 tangential component, and this must be 0 because the system is in equilibrium. Now here, this is the perpendicular component. So the mg sine theta is here, and say m2g sine theta, and the perpendicular component of this, so the angle between them will be 90 degrees, and this term will be 0. The first term is 0 plus, because the dot product of these two, m2g sine theta 2 and drp, this is the angle of cos 90 will come 0. Now it's tangential component. The tangential component is along this side. So there makes an angle 0. The cos 0 is 1. So it will be m2g sine theta 2 delta r delta r 2t. Now here plus this is again perpendicular component of the tension. This will again be 0, and this is under tangential component, but the tension is here and the tangential component is here, making 180 degree. So if you take cos 180, it will be minus. So I am just writing here minus T delta R to T. Again M1G, and the displacement is compared to the displacement, vertical displacement is perpendicular to this. So this gives you 0. And this is the tangential component. So again cos 0, that's 1, M1G sin theta 1 delta R 1T plus this again the perpendicular component tangent on, so this gives you 0 plus this is the tangential component but makes an angle of 180 degree, so it will be minus T delta 1 T equals to 0. Okay. Now, what are the constraints here is that the two blocks are attached by a fixed string. The length of the string is fixed. It means R1, total R is here fixed. So suppose if R1 plus R2, that is suppose here this is here, this is R2, this is R1. So it's R2 plus R1 is say the total length is R. It means delta R2 plus delta R1 will be 0 because this is constant. So the tangential component of delta R2T is equal to minus delta R1T. So wherever there is R6, what's again here? R is missed here. So this becomes M2G sin theta 2 delta R2T tangential displacement here minus del T and delta R2T, okay, minus M1, oh, it's a plus M1G sin theta 1, but delta R1T is minus delta R2T, so it's better to write here delta R2T. So again here this will be a minus R1T will convert into R2T with plus minus sign as it will be plus T delta R2T is equal to 0. So these two cancels out, and we are left with M2G sin theta 2 minus M1G sin theta 1 is equal to 0. Delta R2T common, or we can write that M1G M2 sin theta 2 is equal to M1 sin theta. Get the same result. It seems that this is more tedious than by doing Newton's method, but you will find that in easier problem it is easier to work out in Newton's method, but in complex problem it is easier to work in this system, virtual box system, or you can say Lagrangian system. This is a as it's easier to crack what you call okay, okay, in motion. The system is in motion. So what we got is we have finished with M1G sine theta 1 minus m2g sine theta 2 dot displacement delta r is equal to 0. Now we have in motion Fi minus Pi dot delta r. So if the system is in motion, this force, effective force, is added to it. So it means for the motion we can have to write m1g sine theta 1 minus rate of change of momentum. That means the rate of change of momentum means the acceleration of this particle. So it is minus m1 m. This is f I first part plus or here it's minus, so it's m2g sine theta 2 minus m2 a2 delta r is the total work done is 0. Right, total work done 0, it means this bracketed term, the terms in the braces must be 0. So it is m1g sine theta 1 minus m2g sine theta 2. This will be m1 a, and this goes on that side plus, this is plus, that becomes minus m2. But since the system is connected by a fixed string, so it is A1 and A2. A1 is equal to minus A2. If this is accelerator, this acceleration of this will be opposite to this. So if A1, if suppose A2 is here and A1 is with A1 must be opposed to A2. So this becomes M1 sine theta 1 minus m2 sine theta 2 times g. This will become plus a1, or we can write as a simply. A1 is equal to A2 is equal to, because the acceleration of this and this will be the same but in opposite direction, so let's say it's A. So it will be equal to m1 plus m2 times is equal to, this will be also A, this is also A with but minus. So it, the same result we have found by using Newton's method. Now I will do one more problem. Okay. So I am leaving this the next problem for the next class, because we have already taken a lot of time. And then the next class we will do this one problem, and then we will work out that equation of motion from D'Alembert's principle. F minus I dot delta r. From this we will do solve this equation of motion in terms of generalized coordinates, and that is basically the Lagrangian equation of motion.